Greetings, this is Professor Roman. Let's continue the lecture series in linear algebra. Our goal now is threefold. First, we want to find the primary cyclic decomposition of an operator module. We're familiar already with the primary decomposition. Now we want to take that a step further and decompose the primary summands into cyclic summands. Second, we want to show that the multiset of elementary divisors of every such decomposition is the same. And third, we want to show that the multiset of elementary divisors is in fact a complete similarity invariant. To find a primary cyclic decomposition of an operator module, all we need to do, as I just mentioned, is decompose the primary summands in the primary decomposition into direct sums of cyclic submodules. And they will, of course, be primary because they're submodules of a primary module. But before we get to that, specifically there is a matter we have to discuss, and that concerns annihilating vectors in an operator module using polynomials. So suppose that we have a primary cyclic submodule, in other words, a tau cyclic subspace, and that its minimal polynomial, in other words, the minimal polynomial of tau restricted to the submodule, is a power p of x to the d, where p of x is irreducible. We know, of course, that all vectors in this submodule are annihilated by the minimal polynomial. But what we would like to know is which vectors are annihilated by a given smaller power of p of x. So as for notation, this is what I chose here. I don't believe there's a standard notation. This stands for, this is the set of all vectors in the submodule that are annihilated by the exponent here, p of x to the e. Most of the time we're going to take e equal to 1, but there's no reason to be restrict that now. It's certainly clear that any vector that has the form p of x to the d minus e applied to the generator v will be annihilated by p of x to the e, because that will bring this power, this exponent, all the way up to d, which is the minimal polynomial. So we can say then that all the multiples of this vector, p of x to the d minus ev, are in this set annihilated by p of x to the e. For the reverse inclusion, if we take something from this side, from the right side here, it is of course a polynomial multiple of v, and it's annihilated by p of x to the e. So that means we're assuming that p of x to the e w is 0. That is p of x to the e r of x v. Probably should put the 0 in the front here, and it would look better. And so p of x to the e r of x kills the generator. That means the minimal polynomial has to divide this polynomial. And so p of x to the d minus e has to divide r of x, And so r of xv is a multiple of this vector, and that is the reverse inclusion, and we have equality. So in words, the vectors in this cyclic submodule that are annihilated by a smaller power, p of x to the e, are precisely the polynomial multiples of this polynomial, p of x to the d minus e v. It's worth stopping and thinking about this for a few minutes. This is what you would expect to be the case. And so that'll make it easier to remember this. What about the minimal polynomial of this submodule? Well, it is in fact p of x to the e. Just because everything in here is annihilated by p of x to the e doesn't make it automatically the minimal polynomial. Automatically it tells us the minimal polynomial divides p of x to the e. Okay? But no smaller power of p of x can annihilate the generating vector, and so it takes the full p of x to the e to be the minimal polynomial. Here is the lemma summarizing just what we went through, and containing one additional fact that we will have a great use for. If we have another cyclic submodule, so we have two cyclic submodules, one generated by u and one generated by v, if they are essentially disjoint, excuse me, then the vectors in the direct sum that are annihilated by p of x are the vectors in this submodule annihilated by p of x, direct sum with the vectors in this module annihilated by p of x. So in simple terms, we can distribute this exponent across direct sums. And we're going to do that. And I'm going to let you think on the proof of that rather than go over it, because I think it would be, it's not terribly difficult, it would be a good exercise, good practice. So now we are ready, almost ready. Excuse me, just a little sip of tea. Almost ready to tackle the cyclic decomposition of a primary summand. One of the main problems with the many of the proofs of this, what we would call cyclic decomposition theorem for primary summands, is that it's hard to motivate the flow of the proof. I've seen several proofs, and I went away thinking in each case, where did the steps come from? Each step was relatively simple to understand, but how did the person who wrote the proof put all this together? What was the thinking process behind the proof? Since this is perhaps the least obvious proof in the book, I thought it would be a good idea to try to expose the thinking process for this proof. It does have one downside. It'll be a little bit longer, not much, a little less elegant, because we will come to a point in the proof where we will say, gee, I wish we had done something earlier. I wish you'd made an earlier assumption that would allow us to finish the proof. Well, we just make the assumption at that point, so there's no harm done. But it's a little bit more the way I think a person would develop the proof in the first place. There's a technique used in this proof. And it's a technique we've used before. It's a common technique in proof making. I've never heard it described explicitly. So I'm going to do that now. I call it the extreme witness principle, and that's my own term. You probably won't hear it elsewhere. Speaking in general terms, in mathematics, we often encounter a family, let's say F, of mathematical objects of some kind that are defined by a specific property, which I'll call P. Moreover, we often seek either to find a member of the family that possesses an additional desired property Q, or maybe we're just trying to understand more about the structure of the family. So in either case, if the family is ordered in some natural way, and many of them are, set inclusion, dimension, degree, any sort of reasonable order, then to accomplish our goal, it is often wise to look at members of the family that are extreme with respect to that order. So that would mean the largest or smallest, if such exists, if not a maximal or minimal element, if such exists. And so I refer to this as the extreme witness principle. We've used this principle without mention several times. For example, defining bases for vector spaces. One way to do so is to look at the family of all spanning sets for a vector space and pick an extreme member. Well, the biggest member, of course, is the whole space, and that's not interesting. But on the other end, minimal spanning sets turn out to be very interesting. They are bases. Also, we could look at the family of all linearly independent subsets of a vector space. The smallest members are the singleton sets with non-zero vector. They're not that interesting, but the maximal members are again very interesting. They are also the bases. We use the extreme witness principle to discover or define the minimal polynomial of an operator. We started with the annihilator of the operator. An annihilator of the operator module. All the polynomials that annihilate the whole module. And we chose an extreme member, assuming this is non-trivial. This is ordered by degree, and so there's no upper bound on the polynomials, the degrees of the polynomials that annihilate the module, but there is a lower bound. And so we looked towards the polynomials of smallest degree that annihilate. And we even went so far as to single one out by requiring it to be monic, and we had to prove that made it unique. So the minimal polynomial, as the name would suggest, is an extreme member of a certain family. Okay. Now we are ready to look at the cyclic decomposition of a primary submodule. Here's the theorem. V is a finite dimensional vector space. Tau is an operator on V. We'll let S sub tau be a P of X primary subspace of tau. Actually, I think I'll make that submodule. And here is the minimal polynomial. It's a power of an irreducible polynomial, p of x to the e. Our goal is to find a decomposition of S sub tau into cyclic submodules. And we're going to do that one step at a time by breaking off an individual cyclic submodule, then repeating the process. Here's how you do it. Among all, and again I'm going to make this cyclic submodules, but tau cyclic subspace is fine. Suppose that we take one that has maximum dimension. So we're applying the extreme witness principle. Equivalently, we're taking a submodule that has minimal polynomial of maximum degree, because that's the same as the dimension of the submodule. Then this minimal polynomial is in fact the same as the minimal polynomial of the whole submodule, of the whole module, the whole primary module. And there is a submodule, not cyclic, just a submodule, a tau invariant subspace, a T of S, that is a direct complement of the cyclic submodule we chose. So what we've done here is we've broken off from the original module a cyclic submodule. This is a reduction of tau then. These are submodules. And of course, as I said next, we can do the same thing with T. It's a standalone module. It's primary, P of x primary. We can repeat the process. And so we can decompose our module S sub tau into a direct sum of cyclic submodules. The minimal polynomials are each one divides the minimal polynomial of S sub tau. S sub tau is in fact the least common multiple of those minimal polynomials. So they are all powers of P of x. We can arrange them in descending order or non-ascending order. This is customary but not required, of course. And this is our primary cyclic decomposition for S sub tau. Everything here is primary because S sub tau is primary. We can sum the degrees of the minimal polynomials, or it's the same as summing the degrees of the dimensions of the cyclic submodules. We'll get the full dimension. As to uniqueness, the tau cyclic decomposition is not unique. We made a choice back here when we broke off the first cyclic submodule. We chose one of maximum dimension. Well, there may be several. So while the decomposition is not unique, it's remarkable that this set of elementary divisors, it's a multi-set because some of them may be equal, is unique. Does not depend on the cyclic decomposition. The minimal polynomials are the same, the multi-set of minimal polynomials. So if we have another decomposition of S here, this one was the U's, this is the V's, and if these are the elementary divisors, the minimal polynomials of these submodules, where here Q of x is irreducible, then these two multisets are the same. Okay. So there's the same number of them, r equals m. The irreducible base polynomials are the same, and all the exponents are the same. They're the same. So, proof. Part one is of course the most important part here. How do we break off a cyclic submodule? Okay, so as I said before, we're going to take this sort of as though it was the first time this was proven, and we're going to try to think through the process. So a logical place to start, of course, is just to grab any non-zero vector in the module and look at its cyclic submodule. It's generated by that vector. Our goal is to find a direct summand that's tau invariant, that's a submodule for which this holds. So we don't know this. We're trying to get to this point. Well, there is now a rather obvious use of the extreme witness principle, and that is to choose T to have maximum dimension among all the submodules of the module that are essentially disjoint from U. It's not essentially disjoint, that's not going to be a direct sum. It might be a sum, but it won't be direct. Okay? If it doesn't have maximum dimension in that family, there'll be a bigger submodule that's essentially disjoint from U, so this cannot, while this could be direct, it can't be all of S sub tau. So we don't have any choice, really. If we're going to find a T, it has to be in the family of submodules that are essentially disjoint from U, and it has to be the biggest possible. There may be more than one choice, but those two conditions are necessary. Because T is essentially disjoint from U, we do know that the direct sum exists. Excuse me. And now all we have to do is show that it's equal to S sub tau. So let's assume to the contrary, that it's a proper submodule of S sub tau, and find a contradiction. Well, what's to do but to take a vector that is in the module, but not in the submodule, and not in the direct sum. Let's call it little s. It belongs to S sub tau, as everything does, but it does not belong to this direct sum. We gather as much information as we can about this vector in the hope of finding a contradiction. We don't have a lot to go on. Basically, what we have to go on is the fact that T has that maximality condition, its maximum dimension among the submodules that are essentially disjoint from U. Okay? Well, that together with this gives us something to do. Little s does not belong to T. Therefore, if we construct this submodule, it will be strictly bigger than T. So basically we throw in S and everything we need to throw in to make this a submodule. It can also be written this way. This is what the vectors look like. Polynomial multiples of S plus a vector in capital T. This is strictly larger than T and therefore must intersect U non-trivially. So there's a vector of this form, I called it alpha of x S plus T, that is in U. Okay. This together with the essential disjointness of u and t, imply that, again, that alpha of xs here, if you move the t to the other side, so to speak, belongs to this direct sum, but alpha of xs does not belong to t. Because if it did, then this would be in t as well as u, and so it would have to be 0. Okay, so this is where we stand right now. We have these two facts, all based on the maximality assumption, maximum dimension assumption about t. Now we need, well, maybe a spark of inspiration. We need an idea. And here's the idea. Suppose we could show that the vector p of x s does lie in t. Alpha of xs does not. What if we could show that p of xs does? Why would that be helpful? Well, we would then have these three things. These two are the same as these two. I just recopied them, switched the order for some reason. And this is the assumption that we'll make momentarily and an effort to prove it later. Well, now, p of x is irreducible. P of x cannot divide alpha of x then, because then this would in fact be a multiple of p of xs and would then be in t, but it's not in t. Okay. So with this additional fact, if we can prove it, we're essentially done. We have a contradiction. So assuming this for now, p of x does not divide alpha of x, but p of x is irreducible, which means p of x and alpha of x are relatively prime. And that is almost a mandatory call to Bezos Lemma. Whenever two things are relatively prime, the first thing that should come into your mind is Bezos Lemma. There are two polynomials f and g for which this linear combination is equal to 1, and so our vector s that we're interrogating in the hopes of finding a contradiction is 1 times s splits like this, and that is in u plus t. That is a contradiction. Okay. So, we are left with finding a non-zero vector s in here. I didn't even have to say non-zero because it's not in the direct sum, therefore it can't be 0. We're looking for a vector in here for which p of xs is in t. That's what we're down to. That will complete the proof if we can find such a vector little s. Well, so we've got a family here. The family of vectors is this family. And we're looking for a special member that has this property. Time for the extreme witness principle a second time. How should we choose a vector in here that might advance our argument? Well, we can choose one, a little s, for which this cyclic submodule has smallest dimension, or put another way, the minimal polynomial p of x to some power d has smallest degree. There's no guarantee that S is going to work, but we have to do something to get some more facts, to get some more ammunition. So by choosing a vector S with this property, at least we can move on. Whether it's in the right direction or not, we don't know. Okay. What can we say about P of XS? Well, it cannot belong to the family that we're dealing with here, because its minimal polynomial is P of x to the d minus 1, and we've chosen S to have smallest degree minimal polynomial. Okay, so P of XS, that's after all, we're trying to show it's in T, right? We're hoping to show it's in T. P of XS cannot belong to this set, so at least it's in that direct sum. That's a step forward. What we need to do is try to eliminate the u here and show that P of XS or some other vector we can derive from S belongs to T. So this statement is the same as this. Q of x is some polynomial, T naught belongs to capital T. What can we do with this? Well, gee, if P of x happened to divide Q of x, say Q of x was h of x, P of x, we could take this and shove it to the other side. And so we would have P of x times this vector is in T. This vector, W, does not belong to U plus T. It's in the family that we're studying. And when we multiply it by P of xw, we land in T. We would be done. Okay. We would be done if, where'd it go? Q of x was divisible by P of x. Well, what are we going to, our only ammunition is this formula. Oops, where'd it go? This one. Okay. P of x to the e annihilates everything. So if we hit both sides of this with P of x to the e minus 1, we'll get 0 on the left. And on the right, we'll get this. This is very useful because these two vectors, this is in U and this is in T, and they're essentially disjoint. So if their sum is 0, both of them have to be 0. In particular, this first one has to be 0. Here's Q of x. We're hoping it's divisible by P of x. Maybe we could show this whole polynomial here is divisible by the minimal polynomial P of x to the e. Then Q of x would have to have P of x as a factor. Under what conditions, if you have, say, I don't know, R of x, U equals 0, under what conditions is R of x divisible by the minimal polynomial of the module? Well, if U had maximum, if the submodule generated by U had maximum dimension, or if U had maximum minimal polynomial, or that the submodule generated by U has maximal minimal polynomial, maximum degree, then it would take P of x to the e to kill this. So, final observation to finish the proof of part 1. If we had applied the extreme witness principle to our initial choice of the vector u, so if we had chosen u not just to be any non-zero vector in the module, but to have the property that its cyclic submodule has minimal polynomial of maximal degree, that minimal polynomial would be the full minimal polynomial, because no lesser power of p of x, if it can kill u, that would mean that it would kill everything. In other words, it would kill all the cyclic submodules, which means it would kill all the vectors. So this is the amendment we make. At the initial step, we should have applied the extreme witness principle. It's just that it wasn't clear that we needed to at the time, or how exactly to do it. Now we see exactly how we needed to do it. And so, as I said, p of x will then divide q of x, and the proof of part 1 is finished. This is not an easy proof. It could have been done more elegantly by making the additional assumptions at the beginning, but it would have been harder to see where things were going, or where they came from, really. So I would, if you're serious about improving your proof technique, I would go over this proof a couple of times until the thought processes behind it and the individual steps seem pretty reasonable. Okay. Don't be depressed if you say to yourself, I never would have thought of that. It takes practice. It takes years of practice. Now, as far as the rest of the theorem is concerned, much of it follows from part 1. Part 2 we've already discussed. You just apply the part 1 again to t, and then again and again until you get a full decomposition into cyclic submodules. Adding up the degrees and the dimensions will give you this. The uniqueness part is still something that requires proof, and it's a little unpleasant. Suppose we have two decompositions of s sub tau, and here are the minimal polynomials, the elementary divisors associated with each decomposition. As I said before, the minimal polynomial of s sub tau is the least common multiple of the minimal polynomials of the summands in both cases, and that least common multiple is the first polynomial, so in each case. So p of x to the e, which is the minimal polynomial of s sub tau, is both p of x to the e1 and q of x to the f1, and since p and q are irreducible, they're equal, the exponents are equal. So at least we're off to a good start. The previous lemma, and this is where we're using it, we can take both of these and hit them with p of x, so to speak. Okay. In other words, take the vectors in here that are annihilated by p of x, the vectors in here that are annihilated by p of x, of course they're the same, and distribute the p of x, and we get something that looks like this. Okay. And the dimensions here are the degrees of the minimal polynomial, which is just the degree of p of x. So when we sum these dimensions on both sides, on one side we get m times the degree of p of x. On the other side we get r times the degree of p of x. So m and r have to be equal. So there are the same number of entries in each of these multisets. And we can now write them this way. These are all powers of p as well as these. Same number of them. The first ones are identical. The rest, we still have exponents e here and f here. How do we show e2 equals f2 and so on down the line? By induction. And that's induction on the largest exponent. Okay. If that largest exponent is 1, then there's nothing to do. They're all 1s. All the exponents are 1s. Suppose the result is true whenever the largest exponent is less than k, but we now have a situation where the largest exponent is k. Well, we need to break off some of these. Some of the exponents may be 1 in both cases. And so the corresponding submodules are annihilated just by p of x. So what I did was I said, well, let's say the exponents e1 through em are e1 through es and then 1s. And here f1 through fm is f1 through ft and then 1s. I know there's the same number in both cases, but I don't know that there's the same number of 1s. Applying p of x, multiplying by p of x, gives us these two expressions. So p of x s sub tau has two different decompositions, but now the minimal polynomial has a degree less than it did before, and so the exponent, in other words, is smaller, and so we can apply the inductive hypothesis. Okay. And so what we get is that there are the same number of non-1s in both cases, which means there are the same number of 1s. Okay. And by the inductive hypothesis, the e's and the f's are equal. Okay, that is the full proof. It's a tricky one. Probably why it doesn't appear in many courses on undergraduate linear algebra. Now we can combine the primary decomposition and of an operator module and the cyclic decompositions of each primary summand into one big bundle. This is the primary cyclic decomposition of an operator module. V sub tau is finite dimensional operator module. Minimal polynomial of tau has prime factorization. Looks like this. The p's are monic and irreducible and distinct. Here is the primary decomposition that we've worked with before. The summands are the kernels of the individual prime powers. And the summands are tau invariant, so they're submodules. So we have a reduction of tau. And the minimal polynomials are precisely these prime powers. That is all old news. Each of the primary summands can be decomposed into a direct sum of cyclic submodules, or tau cyclic subspaces. And their minimal polynomials are powers of pi of x for ki here. And so their dimensions are the degrees of these minimal polynomials. And as I mentioned, it's customary to order them this way, the exponents. Piecing the two together, we get this massive decomposition of v sub tau into a direct sum of cyclic submodules, primary cyclic submodules. Gather all of these minimal polynomials together into a multiset. Those are the elementary divisors of v sub tau. Remember, they don't depend. The primary decomposition is unique except for the order of the factor, of the order of the terms. And the primary decomposition, the cyclic decompositions of each primary summand are not unique, but their minimal polynomials are. So this set, this multiset, is completely determined by tau. If we write the degrees this way, we can produce cyclic tau cyclic bases. Their union for each of the cyclic submodules. The union is a basis for the whole space, v sub tau, the whole operator module. The sum of these degrees of the elementary divisors for particular primary summand looks like this. So the dimension of the whole space is the sum of all the dimensions of these guys. So it's a double sum. So the elementary divisors, if you add up all their degrees across all some submodules, you get the dimension of the vector space. This formula, it looks pretty ghastly, but in words it's not so bad. If you have this multi-set of polynomials, they're the elementary divisors, you just add up their degrees. This can be useful in finding the possibilities for the multi-set of elementary divisors in small cases. So let's look at a few examples. If we have a minimal polynomial whose prime factorization looks like this, we'll do this for matrices. Let's say for a matrix A, 8 by 8 matrix. Okay. Then we know that the elementary divisors are all, there's going to be one for each prime factor, prime power factor, and then there may be others with exponents no bigger than the first one. So these e sub i's are no bigger than 3. And there may be repeats of this linear elementary divisor. We know that both of these are included in the multiset of elementary divisors, and that the sum of the degrees of the elementary divisors has to be 8. So there's not much choice. You've already got you've already got 7, so the best you can do is throw in one more of these. And you have to get it to get this formula to work. Whoops. Okay. So the elementary divisors are in fact this one and this one repeated twice. Okay. Here's another example. Minimal polynomial looks like this. Matrix of size 7 by 7. Again, we have to have one of these and one of these, and we have to fill out the degrees, and you can check that easily, leaving 2 possibilities. Here's a little bit more complicated example, 15 by 15, minimal polynomial. So we can say there are, let's say, A copies of this factor here, and A is at least 1. I wrote that somewhere. And there are B copies of a reduced power, but there may not be any. And then there's at least 1 copy of x minus 2. So C is bigger than or equal to 1. Well, it's just, then we have to, this is the equation that adds up the degrees of the minimal polynomials. It has to be the dimension of the space. So we can just find a list of solutions. It turns out that there are 12 possibilities for the multi-sets of elementary divisors. I hope you'll review this video. If this is a bit more complicated than what we've done before, so it's there for you to review.